David, just for the very unlikely case that my internet connection breaks down.
Yeah.
Will I just reconnect, like use the same link? And try to get back in?
I think you should, Fabio.
Yes, you can use the same link.
Okay.
Okay.
Okay. Okay, more people are arriving. May wait a couple of minutes. There's a crowd arriving now.
Yeah, sure.
Yeah. Okay. Okay. Good afternoon, colleagues, ladies and gentlemen. Thank you very much for attending this fourth seminar.
Ora si registrerà, non si sta più registrando la
Geo-energy,
conferenza.
which is being organized by the
Ora
Italian
si
Geological
registrerà la
Society.
conferenza.
And today is my pleasure to introduce you our colleagues, Niklas Heinemann, which is from University of Edinburgh, and he will introduce us to a different aspect of the geostorage, which is very interesting, very challenging, which is now a lot of journal science becoming more and more a hot topic across all the geoscience community, which is about the hydrogen storage in porous media. As every talk, I do remind you that just before we start, that you have the opportunity to be linked across a YouTube channel, which will produce on streaming a registration of the talk. And there the talk can be downloaded or basically registered at your perusal. So you can attend and relook at the talk later on when you prefer. Therefore, today it's the talk about enabling large-scale hydrogen storage in porous media, the scientific challenge, and the speaker is Niklas Heinemann, which I give you a very short overview about his career. He has been graduated in Freiburg, and then he took his PhD at the University of Edinburgh within the Scottish carbon storage capture groups. And since then, he has been working for a couple of years at a company called Icon Geopressure. So he has been working a lot on the topics related to the geopressure, overpressure on the geological media. And after that, he went back again to academia within the University of Edinburgh, where now he is essentially a researcher working in there on a subject which is the problem related to the hydrogen storage and problems related to storage in porous media. I therefore leave the word to Niklas. Fabio, please allow him to share the screen. And have a nice talk to all of you. I see you in around half an hour, 40 minutes for the discussion. Thank you very much.
Right, should there be something?
Can I hear you?
Am I sharing my screen? I have not
Yes,
seen any.
you can. Yes, you can.
Right, okay.
Perfect.
Right, can you see this?
Yes, we do.
Okay, perfect. Right, thank you very much, David, for inviting me and for organizing all this. So my name is Niklas Heinemann. I'm a PDRA at the University of Edinburgh and working mainly on gas storage. So today I want to discuss hydrogen storage in porous media. I myself started looking into this with my senior, Dr. Mark Wilkinson, in 2018. So at that time, Mark had already worked on this before and published a paper as a co-author on storage in depleted gas fields, I think in about 2016. But I properly got involved in this in 2018 when I was still working on CO2 storage. So I'm paid by a project called HyStorPor, which stands for Hydrogen Storage in Porous Media. It's a 3-year project, and we're bringing together researchers from several disciplines to work on this really interesting topic. So I am aware that I'm going to discuss quite a niche geo-energy application here. It's only a very small part of the overall gas storage story, besides natural gas storage and of course CO2 storage, or as well as compressed air energy storage. And additionally, I will focus solely on the storage in porous media, so I will neglect salt caverns. Nevertheless, I will hopefully not make the impression that any of these other options are not worth investigating or implementing. I will not advertise here for hydrogen storage. It's just, what I'm currently doing and what the title of my talk is. So what I will do today is I will try to introduce you to what I think the principles and the challenges of hydrogen storage in porous media are. We will hopefully finish up with an interesting discussion, and fingers crossed, we'll hopefully have learned something after 60 minutes. So this is a slide that I call the renewable energy problem. To push the energy transition forward, we have to do basically 2 things. We have to use more renewable energy, and we have to be more efficient with the usage of energy. And this brings us to this, what I call the renewable energy problem. So this figure has been drawn by my colleague, Julian Castillo. On the y-axis, we see energy, and on the x-axis, we see time. The scale doesn't really matter. And then we have 2 lines here. The red line shows you the renewable energy generation, and the blue line, the energy demand. And you can see that there will always be times when the energy demand is higher than the production, and that means we have to turn on our coal combustion power plants or gas combustion power plants. And there are times when the new renewable energy generation is actually higher, for example, in the summer, than the energy demand. And that means we have to discard the renewable energy. So clearly, what we should do is we should store the energy during times of low energy demand, and then access and use this energy during times of high energy demand. And we think that we can do this, or that hydrogen storage can help us to do this. So basically, hydrogen storage can help to mitigate one of the main drawbacks of renewable energy generation, which is this seasonal variation of demand and supply. So when I say hydrogen, what do I really mean? So how do we produce hydrogen? Let's start with green hydrogen. So green hydrogen is hydrogen from electrolysis using only renewable energy. Hence it's generally speaking emission-free. According to many, this is the future of low carbon energy. On the other hand, we've got blue hydrogen. So hydrogen generated from natural gas by a process called steam methane reformation, SMR. The disadvantage of blue hydrogen is that when hydrogen is created from natural gas and water, something has to happen with the carbon bound in the natural gas molecules. And this will be, of course, released as CO2. So the production of 1 ton of hydrogen produces roughly 10 tons of CO2. This will then be captured and stored in the subsurface with a technology called CCS, the one that Juan Alcalde presented to you last week. So is this carbon neutral? To a certain degree, yes, in a way that you call CCS more or less carbon neutral. But we still, of course, face a leakage of the natural gas production cycle, such as pipelines, leakage, drilling, and so on. So this is kind of, the future. So how the present looks very, very different. The majority of today's produced hydrogen is gray hydrogen, or sometimes called black hydrogen. So hydrogen basically made like blue hydrogen, but without the CCS. So the CO2 will be released in the atmosphere. There are other hydrogen types as well, like yellow, red. There's probably an entire rainbow nowadays, but I'm not going into details here. What I want to point out is that all these hydrogen sources have their advantages and disadvantages. I'm not quite sure what the advantage of black hydrogen is, though. But I would strongly advise you against the notion that we all, for example, love green hydrogen because we are all very green and sustainable, and we don't like blue hydrogen because, we don't like the oil and gas industry. So we should be quite pragmatic here. I would, of course, personally like to see green hydrogen to be developed in the future, but blue hydrogen has some advantages, especially when it comes to like a rapid implementation. It is a very mature technology that allows quick and easy massive production of hydrogen. Right. So how can hydrogen help to decarbonize our society? I've got 4 bullet points here. The first one is energy storage, and this is what I think is most promising and most interesting. So whenever production of exceeds demand, renewable energy that otherwise would be discarded can be converted to hydrogen and stored as a seasonal example, for example, during the summer. It can then be reproduced for whatever application, basically see the next 3 bullet points, which are, the next 3 bullet points are more or less the 3 main energy sectors that we need to decarbonize. So some of them, for example, electricity, is relatively simple to decarbonize, at least here in Scotland, because we have a lot of wind farms. Others, such as transport and heat, are a bit more tricky. Okay, let's start with the gas networks and heat. And what I really mean here is domestic and industrial heating. Here you can already see a difference in country strategies. So, for example, the Germans are quite excited by hydrogen as a fuel to decarbonize the heavy industry, whereas we in Scotland, we are more interested in decarbonizing our domestic heating network by replacing natural gas boilers and run them with hydrogen. So we would be dealing with a lot of very small scale energy sinks. Transport, again, is completely different in terms of vehicle. Electric cars seem to be more favorable right now, but hydrogen might be important for heavy lorries when battery engines simply can't provide enough energy. There has been, discussions on hydrogen-fueled planes. I can't really say anything about this, but to be fair, I would be quite surprised if hydrogen would not become a serious alternative to these heavy, dodgy oil-fueled ships in the future. And of course, finally, electricity. So this is connected to energy storage. So once we need electricity, we can reproduce stored hydrogen and turn it into electricity, which, of course, can then be used for electric cars. And it's important to realize that this reduces, of course, the energy prices as well, and it will increase energy security. So to sum up, hydrogen can help to decarbonize several energy vectors, such as heating, transport, and electricity. And hydrogen can be stored as an option for energy storage. Okay, that's the end of my first part. Let's move forward and discuss the principles of hydrogen storage. So let's start with some basics, and that is the mass and the energy density of hydrogen. Energy density is the amount of energy stored in a material. So at the top right, you see a gray box with the energy density of hydrogen, and as well as the energy density of natural gas and diesel. And you can see that hydrogen has a relatively high energy density, almost 3 times higher than the other fuels. So this is actually quite good and should make the storage of hydrogen a very, very efficient process. But unfortunately, there is another density, which is a bit of a downer. So the big figure in the middle, the big diagram shows you the density versus pressure. So density on the y-axis, pressure on the x-axis of 3 different fluids: CO2 in red, natural gas in yellow, and hydrogen in black. For a temperature of 100 degrees, and for hydrogen it's 40 to 120 degrees. So it's basically about, at least for CO2 and for natural gas, it's 3 kilometers depth. So we can already see that the hydrogen density under subsurface conditions, which is highlighted in this box, is somewhere between maybe 7 and 20, well, maybe a bit higher, kilogram per cubic meter, which is approximately 10 times lighter than methane. So hydrogen will require 10 times more space in the subsurface compared to natural gas. However, as we know already, it also contains 3 times more energy. So just to store the same amount of energy, we have to store around 3 times more hydrogen than methane as volumes. So what do we need in the subsurface to store hydrogen? So this is, basically the simple gas storage play, or in this case, the hydrogen storage play. We of course need a reservoir rock, so a porous and permeable formation where we can inject and store the hydrogen, but also where we can reproduce the hydrogen from. We need a cap rock, that also a low permeability rock that overlays the reservoir, that does not allow the vertical migration of hydrogen. And very important, we need a trap, so that we have to keep the hydrogen in place. The hydrogen must not migrate laterally away from our injection and production well. To be fair, we don't have a lot of direct experience of hydrogen storage in porous media. However, so the storage of what's called town gas, so hydrogen-rich gas mixtures, was quite common not too long ago in the UK, maybe about 50 years ago. And there's a lot of lessons to be learned from that, at least. I think this is one of the research workflows that we should follow. In terms of other research workflows, of course, we can, we have a lot of experience from CO2 storage research, so especially when it comes to, for example, geochemical assessments. And of course, the overall procedure of hydrogen injection, storage, and reproduction is quite similar to natural gas storage, which has been done in porous media successfully for decades. So although this, it kind of sounds very, very, very new and very theoretical and very science fiction-y, we should really keep in mind that we are by no means starting from scratch here, but we can really exploit knowledge and research from decades of, from other or comparable applications. So how do we envision this hydrogen storage idea? So this is a very, very schematic diagram. You can see there's a depth scale that says 1, 2, 3 kilometers. This is of course assumed, but it's important to put that on, because otherwise people will think that we want to store hydrogen just underneath their basements. I really can only recommend to everyone to have this and explain this in presentations, because public perception really matters here. So the basic idea is we've got wind energy that would otherwise be discarded. We turn it to hydrogen with an electrolyzer. we inject it into the subsurface, into porous media, where it is retained by a low permeability rock. And if demand exceeds renewable energy production, we can reproduce it and send it to the consumer. So in the subsurface, we basically have two options. Firstly, we have saline aquifers, which are porous and permeable formations filled with brine. They can be found in most of the sedimentary basins, and they can be very, very large. A good example would be the Bunter sandstone in the North Sea. And we have depleted hydrocarbon fields, so gas, oil, and condensate fields as other targets. They are smaller, generally smaller than saline aquifers, although they are often parts of saline aquifers actually, but especially depleted gas fields have some very, very important advantages. Firstly, they are quite well understood. So sometimes decades of exploration and production has produced enough data, a really good understanding of the geology of these depleted fields. Secondly, you've got infrastructure in place, so pipelines, wells, platforms probably need refitting. However, it is there. And as Juan pointed out last week, this of course comes with a price, because abundant wells that might be in these depleted gas fields can be seen as a leakage pathway. Also, gas storage often requires something that's called cushion gas to maintain the operational pressure. There is the idea that this residual gas in depleted gas fields could be used instead of expensive hydrogen, so that would lead to a cost reduction. Then, of course, as a kind of reassurance, the cap rocks of depleted gas fields have retained buoyant gas for over geological timescales, at least to a certain degree. So I'm not sure, or no, we cannot say, or we cannot guarantee that these cap rocks will be hydrogen safe, but it's a good starting point. And finally, depleted gas fields. A depleted gas field is by nature a field that we have developed and produced buoyant gas from. So in other words, we know that we can reproduce out of the depleted gas field. And the injected hydrogen, for example, just not simply migrates away. So I think this is quite a good reassurance, and I think this makes depleted gas fields strong candidates. I've mentioned cushion gas and working gas a couple of times now. One slide on this. So the working gas is the share of the injected gas that will be reproduced. So that's the part of the gas that we're working with. The cushion gas is the share of the injected gas that will not be reproduced, so it remains in the reservoir. It's got basically two functions. Firstly, it prevents volumes of water to enter the production well, but more importantly, it guarantees deliverability. So it maintains the pressure, or it maintains high pressures. There are no fixed kind of working gas to cushion gas ratio, especially not for hydrogen. It all depends on the scenario. It kind of depends on the structure. It depends on what you want, on the overall project. I always think that a good first order approach is a 50-50 ratio. I should mention that we could theoretically use other gases as cushion gas. For example, we could use natural gas, which is of course present in depleted gas fields, or we could use nitrogen or even CO2, which would allow us an additional sequestration of CO2. But then of course comes with caveats that I'll explain later. Okay, let's summarize the scientific, or some of the scientific processes concerning hydrogen storage in porous media. In other words, what do we have to investigate? I think it's important to highlight that all these processes, or a lot of them, have to be assessed in terms of their effectiveness. So don't forget that we are envisioning maybe 30 or 40 years of injection and production of hydrogen. So it's not comparable to the kind of 100,000 or 1 million years that we're facing in CO2 storage. So what could be, a massive showstopper for CO2 storage, let's say some like mineral reactions might be totally irrelevant for hydrogen storage because of the timescales. So I'm going to give you a very brief summary of our energy and environmental science paper, and I will go through these 6 circles one by one now. So let's start with the caprock. So here, of course, leakage is of special concern. So the buoyancy pressure will be high, or is generally high in gas storage, and could lead to capillary leakage. However, this of course also depends on the fluid rock interactions. So parameters like the wetting angle and interfacial tensions, which are not that well understood for hydrogen, actually, are key here. So we should also really look into fracturing due to the pressure changes, due to the nature of the cyclic storage. And diffusion is often mentioned. However, diffusion is a relatively slow process, but still we have to understand it and we have to quantify it. So let's look at the hydrogen plume. So fluid rock interactions such as, for example, chemical reactions could occur. This could trigger the precipitation or dissolution of minerals, which may change both injectivity and the formation integrity. Another issue is microbial activity. So the growth of hydrogen-consuming microbes is often mentioned as a concern here. Possible negative consequences are, for example, that we have clogging of the fluid pathways by microbes. Also, the loss of hydrogen due to hydrogen-consuming bugs, and the production of corrosive gas as a reaction byproduct. However, I should say, this has also been turned into an opportunity by some companies and some research teams. Right. Finally, of course, the dissolution of hydrogen in the pore water, as well as residual trapping, needs to be understood and quantified. Okay, the next one. So this field should represent the processes due to the injection and production. And this will be mainly, of course, pressure related. So the pressure changes, and that, of course, results in stress changes in the reservoir. But, of course, we can control this by just adjusting the operation strategy. Then we have the working gas cushion gas, or in this case, the hydrogen cushion gas interaction. So the most straightforward scenario would be to use hydrogen as a cushion gas. However, if we decide to use an alternative cushion gas, for example, natural gas, nitrogen, or CO2, we're basically creating a gas-to-gas component interface that will turn into a mixing zone with time. This may lead to the contamination of the stored working gas, in this case hydrogen, which is obviously unwanted. Sorry. Then we have the cushion gas to brine transition zone, which here should be seen as a gas-water interface. Here, most of the water displacement or gas displacement, depending on whether we are injecting or producing, takes place. Again, this can be hydrogen or any other chosen cushion gas, but unstable displacement is an issue here. For example, viscous fingering as well as the dissolution and the residual trapping may lead to the loss of gas. And finally, we have to deal with risk related to structural geology. So the cyclic nature of hydrogen storage will lead to pressure changes, which can, of course, always lead to, or could lead to the reactivation of structures. So this was a very rapid summary of this perspective paper in a very short time. So if you're interested in anything, please have a look at the paper. It contains tons of references with much more detailed articles. Before I move on, I should say that so far I've not heard of any, and our own research has not shown any major showstoppers that any of these, so-called scientific challenges could be a serious problem for hydrogen storage. But of course, we have to keep going here. Okay, one slide on site selection, because I think site selection is important, but I will make only suggestions here on some of the crucial parameters, and my list is by no means complete. We have discussed reservoir rocks, cap rocks, and traps structures already, so let me move on to some other issues, which is the fluid itself. So if you have a look at the at figure A, this graph shows the density of hydrogen, natural gas, and CO2 with depth. And as you probably know, in CO2 storage, we usually allocate like a minimum depth of 700 meters because of the phase change of the CO2 from gaseous to supercritical. So below this depth, CO2 storage just becomes much more efficient. So we kind of say we have to store it below 700 meters. With hydrogen, this potential phase change does not lead to any significant changes in the density. So it just becomes gradually denser. So theoretically, the deeper, the better. This becomes more efficient, but there is no, at least not a theoretical lower limit defined by the efficiency of the process. So let's move on to B, which is reactivity, or which is about reactivity. This is a figure by my colleague Eike, and she's plotted the critical temperature and critical salinity from, I think, 270 hydrogen-consuming microorganisms. The figure shows that above a salinity of about 1.7 and above a temperature of 50 degrees, not much reactivity or not much activity is going on in the reservoir. Hence, from the point of view to minimize microbial impacts on hydrogen storage, sites that plot to the right of this red curve would be preferred. And this, of course, you can do with lots of other reactions. And then you can take your for example, your reservoir and plot them on such a diagram and see whether you're safe or whether you should have another investigation. And finally, C, which is for me kind of the inconvenient truth. So there are, of course, a lot of factors not related to geology, such as infrastructure or distance to the hydrogen sources and sinks. But there is also public perception. As far as I know, hydrogen does not have a very positive image. I mean, everybody is really trying hard to change this by calling it green hydrogen and so on. But nevertheless, a lot of people will think about zeppelins when they hear about hydrogen. And I think, in a way, we have to respect this and really have to take this into account when it comes to site selection. Okay, now the third part of my presentation. How am I doing time-wise? It's all good. So some remarks on the storage capacity estimations of hydrogen storage reservoirs. Excuse me. So I come from I have a CCS background, so I come from carbon storage research. So whenever I hear capacity estimation, I think in pyramids. And we usually work with this scheme of theoretical, effective, practical, and matched capacity estimations. So the theoretical, which is the purple one on the left-hand side, the pyramid on the left-hand side, is usually like the first regional approximation, which gives you a massive number. Then you move up because you gain more knowledge, and you look into greater detail. You come to the effective capacity, which is usually a sum of identified prospects and exploration targets. And then you know more. You finally move up to the practical capacity, which is kind of is a sum of the matured prospects and the candidate sites. So I'm personally always quite annoyed by this, because it kind of it shows you that the more you know about an area, the smaller the kind of capacity becomes. So I'm therefore quite interested in the optimization of these things. But let's get back to the pyramids. So I think this is a very good approach. It's a very good methodology, and I would like, and everything will require improvements and refinements. But at least I hope that you will agree with that this is a good approach. So I've got a pyramid here on the right. You can see where we are. So we are now at the base of the pyramid. So this is a study published by Johnny Scaffidi in 2021. And basically what he's done is he has used the BGS managed CO2 store database, which is a summary of all the potential CO2 storage sites or potential CO2 storage sites around the UK. And he has refitted this to the characteristics of hydrogen storage. It's a really, really good study. It's a really great approach because it kind of shows you what we have and what we can work with. It also, of course, takes into account that we need a trap structure to contain the hydrogen. So it's not just, pore space. Johnny looked into three different types of potential reservoirs. So he looked into gas fields, and he looked into silent aquifers with known structures and silent aquifers without known structures. And for the unknown structures, he used a statistical approach for this analysis. And he kind of calculated the likelihood that a sustainable structure is present. His P50 working gas capacity is more than 10,000 terawatt hours, so it's massive. And he assumed a cushion gas requirement of 50% here. So, this is the base of the pyramid, massive. Another study was published by Julian Castillo in 2020 in Applied Energy. And he did much more detailed selection. So he looked only in a few suitable sites. So he basically looked into gas fields that are really well understood. And he also looked into gas fields or he made sure that these gas fields are directly connected to the consumers by a pipeline that connects the field with the gas terminal and then the consumer. He calculated a working gas storage capacity of 2,500 terawatt hours in the chosen fields, again based on a 50% cushion gas ratio. And it's even if I think this is quite close to what we can call an effective hydrogen storage capacity estimation. And the numbers are still massive. And this is important because it shows us that hydrogen really can unlock the door to low carbon energy usage in the UK, but also that there's no reason to believe that there is a competition for the use of the subsurface, like CO2 storage or compressed air energy storage, you name it. We have plenty of these master fields. There is more than enough. Okay, I want to finish up with the practical hydrogen storage capacity estimation. And I want to use a not so well-known smaller field here. So this is the southern North Sea. To the left, you see England. In red, you see all these gas fields, some of them depleted, some of them not yet depleted, in the southern North Sea basin. I want to focus on this small field called the Galahad Field. I don't want to present a storage capacity estimation of this particular field now, but I want to discuss the parameters that could be involved in the estimation of this. So yeah, this is the Galahad Field. It's relatively small. The production started in the 90s. It has produced about 3 million tons of gas, or 4 billion cubic meters. And using the method of Castillo, this corresponds to a hydrogen capacity of roughly 6.5 terawatt hours of hydrogen worth of working gas. Again, we assume a 50% cushion gas ratio. Okay, so let's now focus on this field and let's have a look at the production history. So this is a production profile of the field. This is, by the way, this is freely available data on the OGA website. On the y-axis, we see the produced gas per month in tons, And on the x-axis, you see the time in years, or the time. And this is a typical profile for a gas reservoir. So it starts very, very high with very high production rates, and then the production rate declines, mainly because pressure in the field declines. So my working hypothesis for practical storage capacity estimations is this. All these calculated storage capacity numbers don't provide us with meaningful storage numbers, because we have to get out our working gas within a certain time frame. So for example, for the Galahad Field, 6.5 terawatt hours of hydrogen storage capacity is based on more or less 25 years of production. However, we don't want to produce hydrogen for 25 years. We want to produce it during the winter, let's say over 3 months. So how can we calculate this? How can we calculate how much hydrogen such a gas field could deliver? And I suppose our best guess is to analyze the field production data here. So let's look into 3 scenarios: a high, a mid, and a low case. So for the high case, I assume the maximum production rate ever measured in the lifetime of this field, which is 58,000 tons per month. For the mid case, I use the production rate after 50% of the gas has been produced, and this is still 26,000 tons per month. And for the low case, I assume a production rate that corresponds to what was produced when the field was nearly empty, so 2.7 thousand tons per month. It's kind of the last hiccup of the field, at least this is how it looks like. So if I now use a very simple natural gas to hydrogen substitution in the subsurface, so I replace, for example, for the high case, the 58,000 tons of natural gas in the reservoir with hydrogen, I can use this as a very, very approximate production rate for hydrogen. I then recalculate this to energy, and of course multiply it by 3, because we want to produce hydrogen over 3 months. And then I get a production rate for these 3 months of 0.75 terawatt hours per 3 month per cycle. And that is roughly 12% of the capacity per cycle. If I do this for the mid case, again, applying the simple reservoir volume substitution, we achieve a production of 0.34 terawatt hours for 3 months. And this corresponds to 5.5% of the overall capacity. And finally, for the low case, what we get is 0.6% of the overall capacity. So what does it mean? So I'd say firstly, I think we managed to achieve to narrow down the pyramid quite dramatically and achieve a practical storage capacity much lower than the effective storage capacity. And secondly, I should really highlight this again. This is a working hypothesis, so this is work in progress. This really is, the methodology is being refined while we are speaking. Hydrogen has very, very different properties in terms of how it moves through the reservoir and of course up the well, and this has to be taken into account. And to be fair, it has been taken into account by some researchers, as you can read in Mark Wilkinson's paper from 2016, or in the AMIT paper from 2016, where Mark was a co-author. Thirdly, and that is the main message of this 3rd chapter of my talk, deliverability matters. So just storing the hydrogen is not enough. We have to reproduce it as effectively as possible. Okay, this is the last slide of the 3rd chapter. So hopefully in the future, we will establish a way to calculate the practical hydrogen storage capacity and produce some more accurate numbers for certain geological structures. But I think what is more important is that, that once we know how to calculate the practical capacity, we also know what the main constraints and the limitations are. So we kind of understand why the pyramid has a pyramid shape. And from here on, we can really start optimizing and find ways to increase the practical capacity. So I think, this is super important. And for me as a researcher, this is super exciting. Okay, that's pretty much it. So the take-home messages are: hydrogen can decarbonize the main energy sectors, and it can be stored in large quantities. There are several scientific challenges. So far, none of these seem to be showstoppers. And hydrogen deliverability of wells, or even entire fields, has to be a part of the capacity estimation workflow. Just as my last slide, if you want to have more information about our project, please go to the HyStopper website. We also have a ResearchGate project website where you can find information. These are the references. I think these are the references of all the papers that I've used in this talk. If you need any papers, any publication access to anything, please just drop me a mail. Right, David, that's it.
Yeah. Thank you very much, Niklas. Thank you very much for your talk. It has been very interesting, very, we'll say, very clear and neatly presented talk. So I believe it is time now to open the discussion. So anyone asking question is more than welcome. As usual, I will try to pick up the question that has been written on the chat. So I will start and now call Giuseppe Bellentani, if he can please connect and ask the question to the speaker.
I'm here. Can you hear me?
Yeah, I can hear you.
Okay. Thanks a lot, Niklas, for the presentation. Very, very interesting. I have a question about the oil field. Are there reasons to exclude it from H2 storage?
I
mean, depleted oil field.
Yeah. So basically, the problem that we have with gas storage in depleted oil fields is that we will have a three-phase situation. That I'm not saying that this must be a showstopper, but things become more difficult to, for example, to simulate and to predict. There has also been, I don't know the details, but there has been discussions whether there's additional problems with microbial activity. But okay. I don't know whether this is true. I think future research has to look into this. I think the main reason why people are not looking in particular in depleted oil fields is because we are so at the very beginning with hydrogen storage, and that you look at the kind of fundamental and like easy access opportunities first, which would be depleted gas fields.
Mm-hmm. Thank you. And another question is about gas field. When you inject the hydrogen, how much is the sweep efficiency of the hydrogen against the methane? In order to sweep the methane, you have some residual methane that can be produced. Is it possible? And in that case, is it a problem to burn both hydrogen and methane?
So again, I mean, this is a super complex question because it also asks for the strategy. So if you store in a depleted gas field, and you produce a hydrogen natural gas mixture, depending on your project, you may not like that. So the mixing in the reservoir is a problem. There will be mixing, but the question is how much mixing you will see. At the same time, there are also projects that discuss the storage of like gas mixtures, like for example of a hydrogen natural gas blend, where you actually deliberately inject a gas mixture into the reservoir, and then you hope that there will be no segregation within the reservoir, and you actually produce same like mixture after your 3 month or 4 month cycle. Mm-hmm. But sweeping efficiency, I think this is, like lab work has to show this, and of course, pilot studies have to show this. I can't give you like a number here now.
And the last question is about the well completion. If it's possible to use old wells, and if there are, if there are problem in recompletion of the well using hydrogen.
Again, I can't give you a yes or no. I know that we are currently writing a project proposal on how cement of the cemented wells reacts to hydrogen. These are good questions, but I don't know. I don't think that many people know the answer, to be fair.
It's something that is under study. But it has to be studied.
Thank you very much. I think there are other questions. Giorgio Minelli, please go ahead.
Okay. Can I ask about the problem of loss of hydrogen due to the microbial activity? That is seems to be a big problem.
Well, I can say I'm not sure whether it's a big problem. So far, our research has shown that it's not a major problem, but also that it can be avoided by careful selection of your storage sites.
So you think the conversion by bacteria of hydrogen into sulfate or methane is not a big problem?
Well,
according to
I mean, I don't know whether you're familiar with the work of, for example, Clauster University or RAG in Austria. They work quite intensively on this, and they use it as an opportunity. All I'm saying is, if you have microbes and if you have the conditions that favor these reactions, then yes, it is probably it can be a problem. But at least, according to my understanding, it is a problem that can be avoided by carefully selecting your sites.
Mainly with reservoir rocks, you mean?
Well, it's temperature dependent, it's salinity dependent. I showed this one figure from Eike Tyson's recent paper, where she showed that not much microbial activity is going on above temperatures higher than 50 degrees, and salinity is higher than 1.8 or 1.7. So these bugs, they work really well under certain conditions, but not that well under other conditions. So you just have to take this into account when you do your site selection.
Thank you very much.
No worries. Thank you.
Very interesting. Philip Salter.
Hello.
Hello. Yeah, we can hear you and we can see you. Please go ahead.
So my question was just, could hydrogen storage sites at the end of their working life, like the end of the 40-year period or however long it is, then be repurposed for CO2 storage? And then could you use that hydrogen storage phase as a way of kind of testing the storage integrity of the reservoir? Obviously, we don't want our hydrogen to leak to the surface, but it could be an interesting kind of synergy between the two technologies.
Well, basically, yes. I mean, well, in a way, this is what you've just described is in other scenarios the idea of enhanced oil and enhanced oil recovery, that you have a producing oil field and then you add CO2 in order to get more oil out. And at the end, you just fill it up with CO2 and you have the CO2 storage site. I suppose you have to double check the hydrogen storage reservoir, before you do your CO2 storage in there, because of course other reactions are going to happen. But I would personally think that a reservoir that has served as a hydrogen storage site for 30 years might be a good candidate for future, like, permanent CO2 storage.
Okay.
Okay, thank you. Thanks.
Cheers.
Any other question? Because I may have a couple of questions to you instead, Niklas. One of my questions is back to the diagram where you were showing the plot of this kind of line, which more or less shows is strictly depending on the temperature, which is the best, essentially ideal reservoir, safe from any sort of heavy bacterial, basically, action within the hydrogen. If I'm not wrong, I remember it was oscillating between 60, 70 to 100 degrees. So if you stay away, depending which is the bacteria involved, which I'm not an expert, I have no idea about, you are basically safe from the microbial effect, basically, that is consuming your hydrogen, more or less. My other question is that within this framework, within this system, what is the behavior of the hydrogen in terms of corrosivity with any of the classical rocks? I will say from salt to, if you are thinking of a salt as a rocks for storing the hydrogen, to classical clastic. Are there studies which identify and systematically explore this kind of reaction? What do we know? Are they relevant?
I'm not a mineralogy or petrologist. So I cannot give you any. I cannot provide you with any links to studies. I'm sure there are some in the perspective paper, because there were some really good petrologists working on this as well. But you're right. Hydrogen, it triggers redox reactions, and for the rock, that means that, for example, hematite minerals or iron-bearing minerals might be affected. I don't know the timescale of these reactions, whether this is important or not. But at the same time, what I find interesting is that you can again use this for your site selection process. So you can, for example, discard areas that have a high amount of iron-bearing minerals from your selection process. You can have a look how the kinetics of these reactions is impacted by, for example, temperature. And if these reactions are only relevant because of the time scale, because of the kinetics at really high temperatures, then you just choose a reservoir that is not that hot.
Okay.
So a lot of this is about finding answers to questions, at the same time being pragmatic and trying to work with what we actually have.
Interesting. Okay, so there's a lot of things to explore. My understanding is.
Yeah.
But my other question is a question that I did ask to every speaker of this kind of series. It is a question more generic, more from, I would say, economically point of view. And the question I'm asking is because there is a lot of discussion at every sort of political level, and to me, most of the time the answers are given with a lot of uncertainty, which probably where we are. The story is that we are putting a lot of effort to move away from the, I would say, hydrocarbon type of energy, which is in fact all the knowledge of this technology has produced a society where more or less all the companies that produce hydrocarbon, sell, distribute, are making money. They manage to make money out of it because it's a very well-known technology. They are very efficient from this point of view, but we know the problem that is producing in terms of changing CO2 content of the atmosphere, etc. Now we want to move from this situation, which is profitable from the company which are involved, into a situation where, by using CO2, by trying to set up alternative reservoirs that are able to store CO2, by in this case also hydrogen, with the idea to reuse, for example, the hydrogen ideally for the big massive truck, or for example, any sort of a machine that is very heavy and requires some motion, in which case the battery will be not at the moment the most efficient way. How much it costs, all this operation? I mean, a company that today want to set up a situation where she is injecting essentially hydrogen, mix it to gas, and then reusing it to essentially reusing it across the energetic system. How much it will cost all the operation? Is it still profitable? I mean, is the industry in needs, or any sort of industry which is a state or private industry in needs of extra money, therefore taxpayer investing on it?
Well, so I can say, well, when we focus just on the storage of hydrogen, I mean, the storage of hydrogen, I don't believe that this is a financial risk in a way that the storage of energy is not a financial risk. I think that is I think important to understand. So, it's not in CO2 storage. No one wants to invest, or not many people want to invest into CO2 storage because you don't earn money with stored CO2. With hydrogen, there is a clear business model. We take hydrogen, we produce hydrogen during times when energy prices are really low, for example, during the summer when we have loads of renewable energy. Produce hydrogen, we store the hydrogen in the subsurface, and once in the winter the energy prices go up, we produce the hydrogen and sell it with a profit. So for me, it is a low carbon version of energy storage.
Okay.
If your question was more referring to the overall cycle of producing hydrogen, green hydrogen, then transporting it, storing it, sending it to the consumers, probably replacing the boiler system, I can't give you an answer. But the question is, if the question is whether it's worth investing into it, the advantage of hydrogen is that we can use a lot of the infrastructure that is in place. When it comes to heating, we are merely substituting natural gas with hydrogen.
Yeah. Okay. I think if there are no more questions, I may have to, as we are getting to the time to close this very interesting talk and discussion afterward. If there are no more questions, I may close this event. But before doing it, I will thank you very much, Niklas Heinemann, for his availability to give the talk, this information in there. There is a last question, just a last question. So I give the chance to it's about monitoring. So any particular monitoring required?
Probably any monitoring will be required, especially at the beginning. No, I mean, this is an important issue. Of course, we have to, when we hopefully in the future do hydrogen pilots, we have to, of course, prove that the hydrogen remains within the reservoir, that we don't have vertical leakage, that the hydrogen doesn't migrate away. So there is quite a lot of monitoring techniques known from natural gas, but especially from CO2 storage. So there needs to be refinements, of course. You know, we have to make sure that this also works for hydrogen. But yeah, definitely required.
Yeah. Okay. I think that was the last question. Thank you very much again, as I was saying, Niklas Heinemann. Thank you also to Fabio Petti and Raffaele Viola for supporting with this platform. Before I close, I do remind you that next week there will be another talk, still on the same subject, but different direction. Is about CO2 capture and storage by mineral carbonation, which is another direction which will be an interesting domain and topics, and will be given by Karabowski. So thank you very much for your attendance, and I see you next week at the same times at around 5 o'clock on this platform. Thank you very much again. Have a nice evening.
Thank you. And thanks, David.
Ciao David.
Ciao.
Non si sta più registrando la conferenza.
Grazie, ciao Davide.
Ciao.